I'll go ahead and introduce myself. I'm Georgia. I'm from Cornell, and today's session is about novel methods in causal inference, Bayesian statistics, and stochastic processes. Our first speaker today is Jason Cho from Cornell University, and today he's going to be talking about locally adaptive random walk stochastic volatility.
All right, can everyone see my screen and can everyone hear me? Okay, all right, thank you. Okay, so thank you for the kind introduction, Georgia. In this work, I'm going to be talking about my research on Bayesian method for measuring variance of time series. All right, so here's the brief outline of the talk. I'll first talk about motivation behind my work, some existing models, their challenges, and our proposed model to remedy those challenges. So methods for estimating variance of time series first came about in the field of finance for portfolio selection and option pricing, but the method has been extended to other scientific fields such as epidemiology, geophysics, environmental science, and management. And this is a list of a few papers, not the complete list of papers, but a few papers that use stochastic volatility modeling for their data analysis. So we're going to work in this following framework. We have Y sub t representing the observed time series, and it decomposes into two different parts. So it decomposes into beta t, representing the mean of the process, and sigma t, which is the standard deviation or the volatility of the process. I'm going to use volatility and the standard deviation interchangeably here. For our purpose, we'll assume beta t to be 0 at all time point for simplicity, but that is currently also on my research, which is to measure time-varying mean and the variance at the same time. But for this talk, our goal is to model sigma t, which is the time-varying variance or time-varying volatility of the observed series YT. So you might be thinking that this is somewhat of a trivial problem in classical statistics, right? So you can just simply take the sample standard deviation from the data, but keep in mind that in time series setting, you only have one data point at each time point, and that's a big distinction to have. So you want to estimate standard deviation at each time point, but you only have one data point to sample from, and it's mathematically impossible to do so because you need at least two data points to calculate variance, right? So you need to do some sort of modeling, and what people have done in the past few decades is use these three somewhat classical parametric models called autoregressive conditional heteroscedasticity, or ARCH model, or generalized version of that called GARCH, and stochastic volatility model. Here is exact specification of the model. I'm not going to go too much detail into it, but one distinction that I want to make here is that SV model, they're all trying to estimate the sigma t. However, the way they're parameterized are different. So for SV type model, they're modeled in terms of H sub t, which is the log variance. So it does this log transformation of the variance, and it models this H of t in this autoregressive fashion. And Arch and Garch directly model sigma t. One common feature of these three models is that they're all autoregressive, meaning that it looks at the previous estimate, H of t. So for next H of t plus 1, we look at the previous H of t. Here, it looks at previous data points, Y sub t, and looks at previous data points as well as the previous estimate as well. So one big challenge that I want to talk about for these three models, however, is that they make a very somewhat restrictive assumption that the sigma t is constant. So let me backtrack a bit. So the conditional distribution of sigma t can change over time. So as we saw from this specification here, they can change conditional on the previous data points, but the unconditional distribution of sigma t has to stay constant throughout all time point. And what people have found out in the past few decades is that that's often violated in a lot of econometrics data sets. So there are some fundamental changes in the volatility process. And what people found out is that when that happens, these three models become extremely misspecified, and the volatility process estimated from these models become very inaccurate. So here are some of the examples. On the left, we have the raw temperature profile of liver as a function of time, and global air temperature from 1880 to 2018. So we can see large variance prior to 1900 and somewhat stable volatility after that. So one might argue that the volatility prior to 1900 is fundamentally different from the volatility one after. So what people have done to remedy this problem is by having the parameter of these models to change as a function of time as well. So instead of having a fixed parameter at all time point, you're going to have parameters that also change over time. So instead of having a fixed mu, you can have mu sub t and so on. The way people have done it is using some sort of Markov switching model. So you can have one set of parameters at certain time point, and another set of time point, you have another set of parameters. And this Markov switching into the Arch and Garch and stochastic volatility model have been explored in the past decade as well. So to give you an empirical example of this would be that before 1900, you have one set of parameters, and after 1900, you'll have another set of parameter, right? Because this has large variance, this has a somewhat small variance. So large variance regime versus small variance regime. That would be the heuristics of Markov switching type models. But there is still a challenge with this model, is that you still have to determine the number of regimes in the first place. Are there going to be 2 regimes, 3 regimes, or 4 regimes? So that could be a challenge. And also the transition between computationally, this is also very daunting as well. So here's what I propose. What I propose is something called adaptive stochastic volatility model, which extends the random walk stochastic volatility model with something called global local shrinkage prior. So 2 key advantages of this model, I'd say, is that it provides a locally adaptive estimate of the volatility process without having to decide how many regimes there are. So it learns from the data how many changes there are happening in the data. Also, it generates a smooth, therefore more interpretable estimate of the volatility process, which might provide a clearer understanding of the underlying patterns and trends. So in the next few slides, I'm going to talk about my model. We first start off with something called random walk stochastic volatility. So random walk stochastic volatility has this observation equation. We have a y of t following a normal distribution with some sort of variance term. But we are looking at the log variance term, like the stochastic volatility term. So we have log variance term now following this Gaussian random walk. This Gaussian random walk means that my next volatility follows a normal distribution centered around the previous volatility. And it has one parameter, sigma h. And you can see how this sigma h controls the trajectory of h of t. So if the sigma h is large, that means we're allowing h of t to vary more. There's a higher chance of large changes happening in h of t. When they're small, when sigma h is small, that means there is lower probability of large h of t happening. And one immediate limitation to this model, you can see, is that sigma h is constant over all time points. So that means that the amount of variation h of t to have is somewhat uniform throughout time. And you can see why this is not ideal, right? So this is a simulated example where we can see that the variance changes with time until time 400, right? So in this case, we want the sigma ht to be large because there is large changes happening. But we want sigma h to be small in this case because there's no change at all in terms of h of t. So sigma ht should be close to 0 here and large here. So that's what we're going to do exactly to extend random walk stochastic volatility. So we are going to say that the sigma ht, instead of just having a sigma h, we're going to have this time varying. However, you can't just do that because now we are now in a high dimensional statistics setting, right? So we have too many parameters to estimate. So what people do is in frequentist setting, you would put a constraint on top of it like lasso, but I provide a Bayesian framework for this, which is, so we put something called global local shrinkage prior on top of sigma h. So I'm not going to go too much detail into this, into the specific shrinkage prior that I'm using. We're going to use something called dynamic shrinkage process. What I do want to talk about is global local shrinkage prior itself. So it consists of two parameters, something called global parameters and the local parameters. So the global parameters is exactly what we had before. Here we had one global parameter that controls the overall variation happening in H of t. But in addition to that, what we're going to do is introduce local parameter that controls the local variation happening in the data set. So this allows the data to our models to estimate local changes more adaptively. So we had this global parameter and the local parameter, and they're parameterized in terms of the log of the variance of the variance. So this is the log variance of the log variance. And it's called shrinkage prior because we are putting a very sparse prior on top of it called Z distribution, which is a heavy tail distribution. And it's shrinkage prior because it's either close to zero or really large. Dynamic shrinkage process is a very flexible framework because we are allowing framework because you might have heard of horseshoe prior, and a horseshoe prior is a special case of dynamic shrinkage process. All right, so this is a comparison between random walk SV, that was our starting point. And what we did was make this parameter time varying and also put a shrinkage, global local shrinkage prior on top of it. All right, next we're going to talk about the simulation study that I did. So to compare our model against the traditional parametric models, we did an extensive simulation study. We generated data from, there are 6 data generating schemes. I'll just call them DGS. DGS 1 through 3, stochastic volatility with 1 regime, 2 regimes, and 3 regimes were used to generate the data set, generate sample path. DGS 4 and 5 and 6, GARCH with 1 regime, 2 regimes, and 3 regimes were used to generate the sample path. And these are the exact specification of the sample path here. Okay, let's direct our attention to DGS 1 through 3. Remember that DGS 1 through 3 stochastic volatility models were used with different regimes were used to generate these different data sets. So we compared our model, ASV, with horseshoe prior and dynamic shrinkage prior against the existing model, SV and MSSV, so Markov switching stochastic volatility with 2 regimes and random walk stochastic volatility. So one thing to keep in mind is that stochastic volatility is the perfectly specified model here. This is the true model. And in this case, MSSV2 is the true model. And in this DGS3 cases, MSSV with 3 regimes will be the true model, but MSSV with 3 regimes were not compared because I wanted to compare how our model compared against the other models when none of the models were a true model. So right off the bat, we can see that our models achieve better MAE than the true models, the existing models when there is no true model here. And when there is a true model, in this case, SV and MSSV2, our models is still able to produce somewhat comparable results. Another thing that I want to mention here is the Markov switching type models, when their regimes are misspecified. So in this case, there are exactly 2 regimes, and this is a well-specified model. This is great, but when they're misspecified, when there's only 1 regime, and when I'm trying to fit 2 regime models, it does really poorly in terms of the variance of the model, variance of the MAE. And we can see similarly that fact here in the DGS3 as well. Similar pattern can be found in DGS 4 through 6. The data were generated from GARCH with 1 regime, GARCH with 2 regimes, and GARCH with 3 regimes. And GARCH with 3 regimes, none of the models were well specified. Our models achieve better than the existing models. MS-GARCH2 is a true model here, and our model is similar in term, slightly worse. And in this case, our does our models do pretty badly, but I would say overall, I think it still does pretty well, because keep in mind that our models are misspecified in all 6 data generating schemes, right? And in all 3 cases, MS-GARCH2, when the number of regimes are misspecified, does pretty badly here as well. Lastly, so in conclusion, we see that accuracy of ASV is comparable to the perfectly specified models. ASV has lower model misspecification error than the Markov switching types. Our models is able to approximate true volatility paths across different data generating schemes with a number of arbitrary abrupt changes. And finally, I applied our models to the existing empirical data set. We have S&P 500 data, S&P 500, and Euro-US dollar exchange rate, and finally, COVID death rate. And on the top, we have our estimates, our model's estimate of the volatility path. These 2 are the existing models. And you can see that our models provide much smooth estimate of the volatility path while keeping all the large changes happening. So I'm biased here, but if I were to choose one of the estimates from these 3, I would choose mine because it's much easier to interpret while keeping all the large changes in place. So overall, we successfully incorporated a global local prior for modeling time-varying volatility. We did an extensive simulation study to show that our model produces comparable results to existing methods. Our model is also resilient to model misspecification. Mind you that in simulation study, our model was misspecified all the way through, but did comparably well. And finally, our model distinguishes itself by producing smooth but locally adaptive output for better interpretability. All right, so thank you for listening. I don't know if you have any time for a question, but thank you for listening.
Yeah, I think we have a minute or 2 for questions if anyone wants to type something in the Q&A.
Yeah, Thomas?
Yes, thank you for the excellent presentation. When you were specifying the local global shrinkage prior, is that specifically is that specific prior distribution such as Laplace or Cauchy or horseshoe prior? Or am I thinking of or is it a different prior from those?
I think you can have, I think the structure of it is the important part. So it has to have a global parameter that is fixed for all sample size, all time point, and a local parameter that is specific to each time point. So the local parameter can follow like any, as you said, Laplace distribution or like a Cauchy distribution. But it's more of a structure of the prior. So you need to have a global parameter and a local parameter. And there are multiple papers that talk about how to choose the global parameter and how to choose a local parameter. So yeah, that's an excellent question. Thank you. Any other question? All right. If not, thank you for everyone for listening.
Thanks very much. All right, so with that, we'll move on to our second talk of the day by Changzhi Ma. Today, Changzhi will be talking about estimation of long-range dependence parameters with stationary increments. And take it away.
Okay, thank you, Georgia. If anyone can hear my screen and hear me? Okay, thank you. Good afternoon, everyone. I would like to share with you my research. The topic is estimation of the long-range dependence parameter with stationary increments. And I'm working on it with my advisor, Dr. Zhang. Okay. So here is what we'll be covering today. 4 parts. Firstly, I will introduce some basic concepts in stochastic processes. And then I will introduce a method, GPH, and how to apply it to stationary and non-stationary processes. The third part is my simulation studies, and then I will end it with the future perspective. Okay, let's get started. So the stationarity, there are two types of stationarity processes. The first one is strong, and the second one is weak. So the biggest differences is that the strong stationarity, we record all of the moments and the joint distributions, they are same all over time. While the weak stationarity, we just record the first moments that keep the same all over time. While the non-stationarity is inverse statement, because the statistical properties, they are different in time. Okay, and this is a definition of the long-range dependence. It is the LRD, and it also goes by long memory. Why we call it is a long memory? Because the ACF function of the LRD decays very slow. It is slower than the exponential decline. So here is a definition. Firstly, we found out the autocorrelation rho k, and the rho k in order of ck to d minus 1. So here the capital C is a constant, not equals to 0, while the k is alike. 2d minus 1, here the d is a parameter. Well, if the d between 0 and 0.5, it is a long memory. And under this condition, the sum of the absolute value of the rho k is diverged. So after the concept of the long-range dependence, here is the concept of the parameter d. So we define the parameter d in this equation, nabla d xt equals to zt. And we choose the d between this 0 and 0.5 because we can make sure the xt is a long memory. And here the nabla d is a difference operator. And on this page, I will introduce the different d's value. We can define the different processes. So if the d is a negative or equals to 0, it is a short range dependence, SRD. And we mentioned it before, if the d belongs to this range, 0 and 0.5, it is the long memory. Well, if the d greater than 0.05, it is non-stationary. And here is the plot. I compare the LRD and SRD. So this is the ACF of the long memory data, and this is the ACF of the short range dependence data. So based on these two plots, obviously the ACF of the long memory data decays very slow. It's slower than the ACF of the short range dependence. And this is the non-stationary. I will introduce a non-stationary processes. It named the stationary increments. And here is the definition. And the R is a parameter of the stationary increments. So if the R is 0, it is a stationary. And R if the R equals to 1, based on the concept, it means that the first difference is stationary. Well, if R equals to 2, it means that the twice difference is stationary. That's the first part. So here, the second part, I will introduce a method GPH and how to apply it to stationary and non-stationary processes. So firstly, I will give a very quick literature review. So based on this paper, the author gave us, there are 4 methods currently to estimate the LRD parameter D. So the first method is graphical method. Here is the RS statistic and variance time plot. But the difficult point of this part of this method is that the estimate of the D is not very good if the sample size is not large enough. The second method is parametric method based on the Afrima model. So the idea of this method is that if we want to have a good estimation of the D, we need to have a good estimation of the other orders P and Q. So it means that if the performance quality of the estimation P and Q, so the estimated D is not very good. The third method is non-parametric method. We estimate D with the minimum prior assumption. And this method named the GPH method because it was introduced by Greg Puter Hudak in 1983. And the last method is the semi-parametric method. This method just combines the parametric and the non-parametric, and we can estimate the D using a likelihood procedure. So based on this literature review, the result is that the GPH method is a better way. So that's why I will use this GPH method in my research. So here is the details of the GPH method procedure. So the first step, we define this equation, the nabla D xt zt, same, we choose the D between this range, 0 and 0.5. So the xt is a long memory, stationary. And the step 2 is that we will use a regression method based on the spectral density of this equation. So here the F lambda is the spectral density of the xt, and the Fz lambda is the spectral density of the zt. Okay, the following is that step 3, we will take a log of this equation, one, a spectral density function, and we will replace the lambda by Fourier frequency omega j, and adding a log periodigram to both sides. So here the in omega j is the periodigram of the xt. So here the b is the slope of the xt of the xj, and the b equals to the negative d. So actually this d is the parameter we need to estimate. And I will emphasize here the m's value. Based on the paper, Greg's paper, he defined the m equals to n power alpha, and alpha be between 0 and 1. The last step is that we will use a least square regressions of the variable, and here is the d hat expression. Okay, so this is the details of this method, and this picture I just summarize the steps we talked to previously. So here, the xt is a long memory and a stationary. Well, this is the highlight of my research, because my research is aimed to apply the GPH method to a non-stationary, to a stationary incremental processes. Well, because the application of the GPH method applied to a stationary has been studied. So here is, I will follow the ideas of this method applied to stationary and just make some different. So the different thing is that in step 1, here the nabla D ut equals to zt. Here the ut is non-stationary. It is a stationary increments. And step 2 is the same idea. I will use a regression method on the spectral density function. And here the Fu lambda is the spectral density function of the ut. Well, step 3 is a challenge part because the ut here is non-stationary, so it is difficult to use the periodigram directly. So the method is that we will use the structure function to estimate the spectral density of the ut. The last step is the same. We will use the least square regression to get the estimation of the d. Okay, so this so the third part is my simulation studies. So there are 2 cases here. These 2 cases just apply the GPH method to a stationary processes, just to verify the estimation of the d is good. So here, firstly, in case 1, I set up the nabla D Wt equals to Zt, and Wt here is a very special case of a stationary. The Wt is a white noise. And on the second case here, Xt is a general stationary processes. And this is my parameter setting up. And this is the true D. True D is 0.3, and the D hat is 0.273. And on the second case, the D hat is 0.314. So based on this result, we can find that the GPH method performs well in stationary conditions. Well, the last 2 cases, I apply the GPH method to non-stationary, to a stationary increment processes. So here, the UT1, it is a stationary increments processes with the first order. So here the D is 1.3. It means that the D greater than 0.5, it is non-stationary, while after the first differencing, it is a stationary. And the parameter D will be equals to 0.3. And this is the D hat. Well, the first case is UT2. It's a stationary increment processes with the second order, and the D is 2.3. It means that after the twice differencing, the D is a 0.3. It is a stationary increment. It is a stationary processes. So this is the D hat. So based on this simulation, we can find that the GPH method is also performs well in non-stationary condition. Okay, so the last part is my future prospects. So first one is that I would like to enhance this GPH method to improve the version on non-stationary cases. And we would like to evaluate its effectiveness and reliability. Well, the second part is the challenging part because I mentioned it before, the non-stationary, it is difficult to use the parallelogram directly. So we will focus on how to use the structure function to estimate the spectral density of a non-stationary processes. The last part is I would like to conduct a real-world data analysis to evaluate this method and providing periodical evidence of its utility. Okay, so that's all for today, and thank you for your attention and time.
Thank you very much. Do we have any questions for the presenter? All right. Well, if there's nothing else, we can just move on to presenter number 3 of the day.
Thank you.
Yep. Thank you so much. All right. Our third presenter of the day is Yueting Wang from University of Pittsburgh. And today they will be talking about a Bayesian finite mixture model-based clustering approach of mixed data with censored biomarkers. And you can go ahead and share your screen. Great.
Okay, sure. Good afternoon, everyone. Please let me know if you can not hear me clearly. I'm Yueting, a PhD student from the Department of Biostatistics at University of Pittsburgh. And my advisor is Dr. Chang, and we are working with Dr. Wang and Dr. Yavis and proposed a new Bayesian finite mixture model based clustering approach of mixed data with censored biomarkers. And today, I'm going to present a brief introduction of our proposed model, as well as show some results obtained from simulations and real data application. So a finite mixture model is an important branch of clustering methods can be applied on data with mixed type of variables. However, many challenges still exist, and our research objective is to propose a new Bayesian finite mixture model for clustering to first handle variables of mixed types, which means both continuous and categorical variables, and second, manage the correlated continuous variables and account for cluster-specific unconstrained covariance matrix. So which means we allow the covariance matrix to vary across different clusters. And third, handle censored biomarkers subject to limits of detection. And last, provide quantitative variable importance measure for further variable selection. And so here, we first present the density function of a single subject used in our model. So we assume we have G clusters with M variables in total, where only the first Q variables are continuous and others are categorical. And so we can see that the density function is composed of 2 parts, and one from the continuous data and the other from the categorical data. And we assume all continuous variables jointly follow a multivariate normal distribution. and cite cluster 1 as the reference cluster with the mean vector denoted as A sub 1. And so for any other non-reference cluster G, we let the mu sub mg to denote, denote its mean difference of variable m between the cluster G versus the reference cluster 1. And sigma sub G denotes the covariance matrix in cluster G. And for categorical variable m, we let theta sub mg denote its categorical probability vector in cluster G. And given the cluster membership of the subject I, we can derive the conditional density function by replacing the mixture probability vector with the cluster membership indicator vector, which is the Z sub I here. And to apply Gibbs sampling for parameter estimation, we add conjugate pairs for different parameters. So for mixture proportions, we add a Dirichlet pair, which is the conjugate pair of the multinomial distribution. And to account for unconstrained covariance matrix in each cluster, we add an inverse V-sharp pair for the continuous data. And to measure the variable importance, we add a spike and slope normal pair centered at value 0 on mean difference between a non-reference cluster G versus the reference cluster 1. And we also introduced a dummy variable, the delta sub mg, to indicate the importance of variable m in separating cluster G from cluster 1, the reference cluster. And so greater mean difference between cluster G versus the reference cluster 1 suggests higher variable importance. And if delta sub mg is a zen with a value 1, it means that the mean value of variable m is very different between the cluster G and the cluster 1. And then we will add the slope pair with a very large variance, which spans widely across the value of 0 and on the mean difference of variable m between cluster G and cluster 1. And so the mean difference is likely to be updated by a value that is greatly deviating from 0. And by contrast, if the variable importance indicator, the delta sub mg, is a zen with value 0, then it means that the mean value of variable m is not different between cluster G and the reference cluster 1. And then we will just add a spike pair with a very small variance which spikes near 0. And so the mean difference is likely to be updated by a value close to 0. And the figure 1 on the right side demonstrates the contrast between the spike and the slope normal pairs centered at 0. Oh, sorry. And for categorical variables, we incorporated a spike and slope Dirichlet pair on categorical probability vector. So here we use the difference between categorical distribution within cluster G versus the overall marginal distribution across all clusters to define the variable importance in separating out the cluster G. So greater difference still suggests higher variable importance. And if the variable importance indicator, the delta sub mg, is a zen with value 1, it means that the categorical distribution of that variable m, within the cluster G is very different from the overall marginal distribution. And then we will just add the slope pair with all concentration parameters equal to 1. And so the within cluster distribution will be updated different from the marginal distribution. And by contrast, if the delta sub mg is a zen with value 0, it indicates that the categorical distribution in cluster G is not so different from the marginal distribution. And then we will add the spike pair, the spike Dirichlet pair with concentration parameters that is higher than value 1, but also proportional to the overall marginal distribution, so that the within cluster distribution will be updated close to the marginal distribution. And we also added a beta pair for the variable importance indicator variable to control the shrinkage degree of important variable selection. And for each variable, the overall variable importance measure is calculated by averaging variable indicator across different clusters. And figure 2 here presents the overall Bayesian framework of our proposed model BFMM-VVV. And we use Gibbs sampling in parameter estimation since all pairs are conjugate, and use MAP estimates to assign the final clustering membership. And to handle the censored biomarkers in each iteration of Gibbs sampling, prior to updating parameter values, we first update each censored continuous biomarkers by sampling values below the lower detection limits or above the upper detection limits from the remainder of the truncated multivariate normal distribution, respectively. This is how we handle the censored biomarkers using our proposed model. And next, I will present some simulation results of our proposed model. So we performed simulations in a setting of 3 balanced clusters with a total sample size of 300 subjects. And we cite 7 continuous variables, where variable 5 to 7 are noise variables. So they all have equal mean vector across the 3 clusters. And as to the covariance structure specification, we first set 3 different covariance matrices with varying volume, varying shape, and varying orientation, so that we can further generate 3 different data sets or with different covariance structures. So you can see that in data EEI here, the covariance matrices are all with 0 correlation and also identical across clusters. And in data EEE, covariance matrix are with non-zero correlation, but still identical across different clusters. But in data VVV, covariance matrix are unconstrained and varying across the different clusters. We also cite 7 categorical variables, where variable 10 to 14 are noise variables with a same categorical distribution across the 3 clusters. And we further cite 5 different simulation scenarios. So the uncensored data with EEI, EE, and VVV covariance structure. And for VVV covariance structure, we selected 2 dominant variables, and 1 noise variables to do the censoring, and also cite 2 different levels of censoring proportions on each censored variables as 20% and 40%. And in each simulation scenario, we run 100 Markov chains, each with 500 iterations with 100 Boolean. We then compared the clustering performance of our proposed model with other clustering approaches for mixed data. So this table summarizes the median ARI adjusted rand index out of the 100 random simulations. So a higher ARI value indicates better matching between the clustering results with the true cluster membership. So we can see that across the 5 different simulation scenarios, our proposed BFM and VVV yield higher ARI than most comparable approaches. And this figure presents the bar plots of estimated variable importance of different scenarios. So with the blue colored bars for true dominant variables used to cite the clusters, while yellow colored bars for noise variables. So we can see that true dominant variables are correctly identified and estimated with much higher variable importance than noise variables. We further applied the proposed model on a real clinical data set, which is quite large with more than 20,000 subjects, the Seneca data set with 28 variables, 26 continuous and 2 categorical. We first plot a BIC curves and select 4 as the number of clusters by finding the elbow point of lower BIC values here. We then cite different values of variance ratio for spike and slab normal pair added on the between cluster mean differences and compared the estimated variable importance, clustering results, and BIC. So from table 2 here, we can see that clustering results and the BIC values are almost the same, even if giving different ratio values. However, from variable importance bar plot on the right side, we can see the different ratio values yield different variable importance estimation results. And we select the GCS, chopping respiration rate, and SBP as the top important variables, since these variables are with high estimated variable importance across, even if giving different ratio values. So to conclude, simulation results show our proposed Bayesian model could account for cluster-specific covariance structure to improve clustering performance, as well as handle sensitive biomarkers to yield stable results. But for measuring variable importance, our model correctly identified true important variables in simulations. But in application on Seneca data side, we noticed that the different values of the spike and the slab normal pair variance ratio can differently affect the final variable importance estimation results. So in our future work, we plan to add more simulation settings by introducing the correlation among categorical variables and continuous variables, as well as introducing the imbalanced clusters in simulation data sets. We are also working on exploring how to properly select the value for spike and the slab normal pair variance ratio to more accurately measure the variable importance. And thank you for watching. That's all of my presentation. So does anyone have any question?
I have one question. So do you use Stan to fit the model, or do you, what kind of software are you using to fit the model? Or like what kind of Markov MCMC type stuff are you doing to fit the model?
I used the R code. I just used the R to read the code since we use the Gibbs sampling, we add the conjugate pairs so that we can just derive the posterior distributions. And with the posterior distributions, you can just update the parameter values. So I actually finished all the work just by R.
I see. So you have like a custom Gibbs sampling, like, but like you have a very like slap and slap and spike priors are really hard to code up. So like I was just wondering, like, do you have like a closed form solution to the Gibbs sampling?
Yes.
Or do you
Yes, we
I
have
see.
closed.
I see. Okay. Thank you.
Thank you. So here is a question from Thomas. Has the Chinese restaurant process been considered as an alternative to the dirigible process? No, we have not tried such things. Actually, it's first time that I know this term, Chinese restaurant process. I will look into that.
All right. Well, if there's no other questions, thank you so much for presenting.
Okay, thank you.
Yeah, thank you. So that brings us to the end of session 3.